I wanted to start by just working through some of the kind of the organization of the class and the structure of the class and sort of the goals of the class. And once we've done that, we'll get on with the first couple of assignments for the class, and you get a better idea how the class is going to work with that, I think. Okay, so this is just a list of the things you're going to need for the class. One is obviously access to the class on Canvas. So on Canvas, I'll post the lecture material. I'll post the things like the assignments and other sort of code samples, and also grades. It'll all be done through Canvas. So you'll need that. Like to see a lot of laptops, because you need your laptop. I mean, it can be a Windows laptop or a MacBook, or you have a Linux laptop. They're all just fine. We're going to work with Python. We're going to work with Jupyter Notebooks, and the two most straightforward ways of if you haven't already done so, using Python and Jupyter Notebooks is either through Google Collaboratory, where you just access using wireless, or by downloading Anaconda. So either of these choices, right, or both of them, give you all the materials you need for the class. Give you Python, give you the Jupyter Notebooks, and that's what you'll be working with. There's no textbook required for the class, but I have put, there are sort of online free textbooks, so I put some links in a Canvas page. And I put some links to other things like Python libraries and so forth on our Canvas page. Any questions on that? Okay. So the way I was going to organize the class is that typically we have like the mini lecture at the beginning of the class that I'll use to introduce some sort of physics problem or physics problems, and also introduce some sort of computational or mathematical techniques for solving those physics problems. So that'll be the mini lecture bit, and then there'll be an assignment or assignments associated with the class that are associated with those physics problems and those computational methods. And then the remainder of the class, you can use the class time to work through those weekly assignments. So the assignments are really to further explore and further examine the physics material and the computational methods that we've introduced. When you do the assignments, you'll do the assignments using the Jupyter Notebook environment, and you'll submit your assignments as Jupyter Notebooks. And so the structure will be that each week, so in our Monday class and our Wednesday class, there'll be assignments with the Monday and the Wednesday class. And then the Jupyter Notebooks for those Monday and Wednesday classes will be due the following Monday. So the assignments for today and the assignments for Wednesday, so it's 22nd of August, yeah, and 24th of August, they're due 29th of August. And then we'll just keep on rolling with that cycle. So your entire grade will be based off these weekly assignments and these Jupyter Notebooks. And I just made all of them, they're all just worth 10 points. All the assignments are just worth 10 points. And typically I'm collecting 2 assignments per week. I think this week there's 3. And then your final grade will just be based on your cumulative score on the assignment. So A is 90% or above, B is not 80% or above, and so on and so forth. There's no midterm exam, there's no final exam. It's just these Jupyter Notebook assignments. Is that all clear? Okay, so something about course content. So the focus, I'll just go through the bullets. The focus of the course is really on the physics problems and on the computational mathematical methods to solve those physics problems. So really not a programming course, it's really a physics problem course, a sort of computational physics course. So over this first couple of weeks, I will introduce the sort of Python programming and sort of tools of data science, but really the bulk of our work is on physics problems. I kind of think of physics coming in these 3 branches, or often we think of physics coming in these 3 branches. So, you know, there's theoretical physics, there's experimental physics, and there's computational physics. And the thing about computational physics, it kind of really expands your ability to look at problems. It expands your ability to go beyond sort of pen and paper or pencil and paper problem solving. So that's the real advantage of computational physics. And it's actually, you know, it's easy to get I got the idea from high school, I guess, that, you know, physics problems are always solved with pen and paper. But most physics problems are unsolvable with pen and paper. But most physics problems have to be solved computationally. For example, you have to take a simple pendulum. It's very easy to turn a simple pendulum into a problem that is a simple pen and paper problem into a problem that involves chaos and bifurcation and all sorts of things, where you need computational tools, you need computational methods to solve it. So that's a kind of the focus of this class. So as we walk through the semester, we're going to be applying a lot of the methods of computational physics to, we're going to be using linear algebra, computational physics. We're going to be looking at solutions of ordinary differential equations, partial differential equations, using computational mathematical techniques. We're going to be looking at random processes using computational mathematical techniques. We're going to be looking at more sort of analysis things where we do Fourier transforms, where we do signal processing, where we do data physics fitting to solve physics problems. So this is really the sort of the work that we'll be doing over the semester. We're going to pick problems from all sorts of different areas. So we're going to pick problems from mechanics. We got that today. We'll pick problems from electricity, from magnetism, optics, thermodynamics, and so forth. So we're going to just try and grab different physics problems to advertise different computation methods from all sorts of topics. So the main reason that we're going to use Python and we're going to use Jupyter Notebooks is kind of they're really rather easy to work with. They're really rather easy to learn. And so they're kind of divorce us from having to spend a lot of time learning how to use some computational language or learning how to use some tools, that we can really focus on the physics problem solving and can focus on the sort of computational methods and tools that we'll be using. So just as a quick overview, I mean, many of you probably know Python, work with Python, and probably more than half of you know Python better than I do. But for the rest of you, which maybe none of you, then let me just say a few words about Python. So it's pretty powerful for physics problem solving. It has a lot of the components that you need for physics problem solving. So it has, you know, ordinary numbers as well as ordinary numbers. It has complex numbers, it has vectors, it has matrices. That's very useful stuff for physics problem solving. It has a lot of libraries, a lot of packages that help us with physics problems. So libraries for scientific libraries, statistical libraries, visualization libraries. So that's very helpful for physics problems. And so it's sort of really become Python, I think, the sort of go-to environment for sort of exploratory physics problem solving. So that's why we're using that. Jupyter Notebooks is just handy, famously disorganized. Jupyter Notebooks are handy for keeping us organized. So Jupyter Notebooks you can use you can write your code, you can document your code, and you can document the results, the graphs or the plots that you've got, the tables that you've got from your physics studies. So that's why we'll use Jupyter Notebooks. And as I say, you can either use Collaboratory, and everybody's using that already, or you can download Anaconda, which is a distribution. Oh yeah, forgot this one. Okay, so first classes. So the most important goal for today's class is that we all write a Python code that prints out hello world. So that'll be a big step forward for the class if we can do that. The main goal for this week is to introduce Python language, the important tools of Python language that we're using. So sort of introduce things like variables and assignments, arithmetic calculations, input and output. So we'll be doing that this week. So that's a goal for the whole week. Just as an example, we're going to work with Galileo's free fall law today, and in the associated assignment, you'll work with Newton's law of universal gravity as an example of these sort of arithmetic calculations in Python. So that's the sort of physics problem behind what we'll be doing today. Next week, we'll talk a little bit about sort of more generally data science and data mining. So we'll introduce some of the tools for data science and mining. We'll talk about arrays and lists. We'll talk about libraries for plotting data. We'll talk about libraries for kind of mining data, and so on and so forth. Next week, I think we'll look at some data on sunspots, and we'll look at some data on stellar luminosities as examples of sort of data science. Then beyond that, we'll get on to much more rigorous physics problems. So we'll look, for example, at the pendulum. We'll start just with a simple pendulum, but we'll see how quickly we can make the simple pendulum much more complicated. And we can see, for example, things like that you need computational physics for, things like chaos in a pendulum system. And so that's basically the idea of the next couple of weeks, and then we'll get into these bigger physics problems.